The homework will be due on next Thursday, that is November the 4th, and everyone has a chance to submit your homework late without penalty, but you still have to be able to submit it within 36 hours past the deadline. Okay, so let's compare between the electro and the magnetostatics. So in the electrostatics, the laws are governed by the first two equations, while in the magnetostatics is governed by the second two expression. The E field has a source term in charge density, and the B field has a source term of current density. So in the E field, because del cross E is 0, that gives us rise to a scalar potential V, and likewise for B field, del dot B equals 0, that gives rise to a vector potential A, that you can always write down a vector potential A such that del cross A equals B. And this is guaranteed by the Helmholtz theorem in the first lecture, so you can review how we obtained this by going back to the videos earlier. And now we can see actually that if we write down the expression in vector potential, the vector potential takes care of the del dot B equals 0 automatically, because the divergence of a curl is always 0. So just like how we made use of the scalar potential V, for the scalar potential, the del cross del V is 0, and the scalar potential automatically takes care of this cross product as well. And now if we write down the Ampere's law for the vector potential, simply del cross B equals replace the B by del cross A, that's del cross A, and so this vector identity equals to del dot A minus del square A, and we have to equal the right hand side as the mu naught J. So if you remember that the scalar potential for electrostatic problem, you can always add an arbitrary constant, where the V, del gradient of V remains unchanged. And here, similarly, for magnetostatics, we can add gradient of a scalar function, and the del cross A remains unchanged. The curl of a gradient is always 0. Sorry that I have a typo. Now this means that we actually have a freedom, quite a bit larger freedom, to choose this scalar vector potential A, and this is called a choice of gauge. So we can always choose the scalar potential lambda such that we arrive at a Coulomb gauge, that is del dot A equal to 0. And if we work in the Coulomb gauge, that is del dot A equals 0, then the expression here actually simplifies greatly to minus del square A equals mu naught J. And this is actually the vector version of Poisson's equation. So in the Cartesian coordinate, the Ax must be determined by this mu naught Jx, and likewise the Ay and Az and are also determined by the Jy, Jz. So instead of solving one Poisson's equation, here we simply need to solve 3 sets of Poisson's equation that are independent of each other. then we can determine this vector potential. So now we can simply write down the solution to this vector potential here, because we know that for a localized charge distribution, the V field can simply be written as the rho over separation vector and integrating over all space. And likewise here for the vector potential, we simply need to integrate over all this localized current and divide by this separation vector. So the separation vector is the vector between the source and the observation point. So we can apply this expression to a line current and the surface current. So in this case, the three-dimensional integral simply becomes one-dimensional like here, or it becomes two-dimensional like here. However, I want to note that even though the vector potential here is quite similar to this scalar potential in the electrical static problem, however, the caveat is that because this is a vector potential, so this doesn't really simplify our problem. So in the electrostatic problem, we like the scalar potential because the scalar potential is really a number, and whereas the E field here is a vector. So the number simplifies over this E field tremendously, and we don't have the privilege here that even though we go to the potential form, the potential is still three. It still has three numbers and it's a vector. So it doesn't really help us too much when we try to solve for this magnetostatic problems. But yet we still want to use this vector potential, because this vector potential is really theoretically very important. So for example, this vector potential plays a role in special relativity, and the Maxwell's equations are actually extremely concise and beautiful if you write in terms of all these potentials. So now here, the first equation here simply summarizes the equation for the electrostatic problem. Because here for the potential here, so we should actually we are more familiar with the potential being V, but here this is also here this phi is also the same as V, and this scalar potential actually already summarized the curl of E and the divergence of E. So this first expression is already responsible for two equations in Maxwell's relationship, and this equation is also responsible for the other two of this Maxwell's equation. And however, the difference is that this is written down in the Lorentz gauge, so it's a different gauge than the Coulomb gauge. And now in this Lorentz gauge, you can see that the two actually share the exact same form, and we don't need to treat the scalar potential and the vector potential separately in terms of the Maxwell's equation. And you can sort of imagine that now we can actually write down this scalar potential and vector potential together as a full potential, and this set of equations describing this full potential will be easy to and it will help us in the special relativity. I guess that will be talked about in the second chapter of Griffiths. And this vector potential will also appear in quantum mechanics. So if you write down this Hamiltonian, the this vector potential is related to the linear momentum, and you can actually see it later. That I'll give an example. Now let's try to get some sense about the vector potential. So I said earlier that the equations equation here is for a localized current, and because for delocalized currents you might somehow encounter some divergence, and this equation might not yield you anything. So here I'm trying to give you this example. So here now if we consider an infinitely long straight wire with current I that extends to infinity, then for this current, if we try to find out the potential, then we can first try to write down this scalar vector potential using the formula above. So now if we write out this explicitly, say that we use the cylindrical coordinate and denotes the radial distance as s, and here this is the observation point, and here is the source coordinate. So this is the separation vector, and the current is following to the right. So this equation is simply copied from above, and now if we plug in all these numbers, so the separation vector is simply say this is the along the z-axis. Then the separation vector is simply s squared plus z squared, and along the z hat. Now for this integral actually cannot be evaluated. Because if you plug in this infinity and the minus infinity, this integral is this expression is indeterminate, and so somehow we only know that the vector potential should be along the z-axis, and we don't know how does this vector potential look like if we simply use the expression above. So what we can do next is to use our requirements that now from here we know that the vector potential here must be along the z direction, and we also know that the vector potential must be able to be written as the del cross A form. And lastly, we also work in the Coulomb gauge, so the del dot A must be exactly 0. So if we can somehow find vector potential satisfies these equations, then we know that has to be the solution that we are looking for. So Now let's try to write down this B field. So the B field here is del cross A, and if we so the B field here can be calculated using this Ampere's law, and if we define a circular loop that circles this straight wire, we can know that this B field is across this azimuthal direction, the angular direction phi. And now this B field must be written down as the del cross A. And if we write down this del cross A in the cylindrical coordinates, we get the expression here. Here, right on the right hand side, I'm simply writing out the del cross term in the cylindrical coordinate. It's slightly different from this Cartesian coordinate, and notice here there are 1 over s and 1 over s here, because of the line element, and we will provide this information like during the exam, though you can look up this on the first page of Griffiths if you are doing homework. And now if we take a careful look at this expression, let me see. So here this A must be the A must be along this Z axis. So this A phi must be 0, and A phi must be 0, and here the AS also must be 0, and the AS must be 0 as well. And here this AZ, if we look at the expression above, you see that the AZ doesn't depend on this angular direction. So here this term is also 0. We can also see that on the left hand side there is no S direction, so there is only the phi direction. So now if we compare the left and the right, we know that and from here we can simply see that the AZ must be and there can be a constant. So to double check if this is a correct vector potential, we can try to see if this del cross A is 0 or not. If it's 0, and then this vector potential should work, and that should be the solution. And if it's not 0, and then you might need to add additional scalar potential to to be correctly in the Coulomb gauge. Okay, so now let's take another look at the example, and this example is different from the above one in the sense that here we are considering a rotating spherical shell. So this is the source is a finite size. So because of this property, we can simply use the equation above about the from the source terms, integrating over all the source terms, and we know here we are considering a uniform surface charge, and the charge is rotating, so will generate a surface current. So instead of writing in three-dimensional volume current, we instead write down the formula in terms of the surface current here. In principle, if from this expression we can obtain this vector potential, and the problem is to consider a rotating spherical shell. So here there is only a shell of charge, and this shell of charge moving will generate the surface current. Here, then this surface current is simply the surface charge density times the velocity of this charge. And you might be tempting to work in the spherical coordinate and setting up the axis such that the rotational axis is along the z-axis, just the left-hand side. And in this case, then we need to consider a source term that can be here, and observation point at another place. And it turns out that somehow it's actually easier to calculate the vector potential if we rotate coordinates on the right hand side. So instead of aligning the rotation to this z-axis, we align the observation point into the z-axis. And this is simply some numerical trick. And now if we rotate the coordinate system to the thing on the right, then we can write down this first we can write down the separation vector. So the separation vector is always the distance between the source and the so the numerical trick is to align the final observation point along the z-axis instead of the here. One naive choice will be simply to align the z-axis to the rotational axis. So here on the right hand side, the rotational axis is off the z-axis. So here the separation vector amplitude is simply the source will be always on the radius on the shell of this sphere. So it's the r squared, and the observation point is the r vector. So the distance between these two vectors is the here, and so this cosine theta prime is the angle between the r and the r prime vector. Now, the velocity of this volume element should be this omega cross r, and because the sphere is rotating according to the omega axis in the frequency of omega, and here this omega is being put into the x and the z plane. So omega. So this omega has the x component, and also has the z component. Now we can write down this cross product explicitly. So the r prime written down in the spherical coordinate is simply so the r prime is defined by the r prime, theta prime, and the phi prime. So in this spherical coordinate, now let's write this out explicitly. So there will be terms along the x, y, and z axis. And this integral, so this expression actually not as difficult as it seems, because here the integral of the dA can really be written as two parts. So the first part is the integral along this d theta, and another is d phi. And for this d phi integral, we can take a look at the terms involving. So if you notice a term that's sine phi prime, d phi prime, or if you notice a term of cosine phi prime and d phi prime, then these are exactly zero, because the integral is simply cosine phi prime and sine phi prime evaluating at the same point. So that helps us eliminate the this term if we do the integral, and also the term here, and the term here. So as you can see that there actually is only a single term remaining. So now if I write down the A field, is simply the And here what we left over is a single integral along the theta prime direction. And so we already performed the integral along the phi prime. And along the theta prime direction, the integral in the parentheses is actually something we are familiar. I believe in lecture 1, we did a similar integral, except that in that case, we don't have this cosine theta prime. And in this case, we have an additional theta prime in the integral. So in principle, this integral can be done mathematically. So without any input from the physics side. So if you can replace this mu, if you replace the cosine theta prime by mu, then this integral is being translated to this and this integral can be again be done by replacing the t to then you can replace mu by t and working out dt the mu and du, and then you will arrive eventually at an expression like this. So this is in principle can be done from pure mathematics, and now you see, if you remember that when we did the integral of the expression here without the cosine theta prime, we also had this absolute values in the second lecture, and this is similar here. But now, since you already know something about the physics behind this integral, so here we can actually see that on the bottom side, this is simply the separation vector. So this is exactly equal to this 1 over separation vector, right? And now this separation vector is known to be expanded in this Legendre polynomials. So and now what's on the top here is one term involving the cosine theta prime, another is the volume element. So this cosine theta prime is simply the P1 cosine theta. So now this integral is actually has some physical meanings in the sense that here let's simply define this as f. So here this f is simply the integral of -1 to +1 of so we write this cosine theta prime as the P1 cosine theta prime. So now according to the orthonormal relations, we can immediately tell that in all these sums, only the L equals 1 component contribute. So this integral actually can be simplified into a single term only. And in the end, we get the R prime over R prime. And the normalization factor is 2L plus 2 over 2L plus 1, so it's 3. And however, we have to be careful that the R prime over R is should be less than 1. And so otherwise, this theory doesn't converge. And so here we have to assign what's the sorry, I actually should be more careful of say I'll denote the so here this R prime and R simply some dummy index, because we don't know which one is R prime and which one is R yet. Because you can sort of see that in this denominator, the R and R, little r and capital R doesn't distinguish between each other. So we have to assign the larger ones to this R prime, and the smallest one, the larger one to be R naught, and the smaller one to be R prime. So in the end, the result should be 2R over capital R squared over 3 if R is less than R, and 2R over 3R squared if R is larger than R. So if you carefully check the expression over here and over here, they are actually equivalent. Now from this expression, after we done this integral, we then can figure out the A field. So the A field, vector field, will eventually be something like this. So in principle, first we will get the A field that's along this y direction, right? Because initially we see that the A field is along the direction of y. So here A should be along this y direction. Now let's try to write this A field in terms of the coordinate-free expression. So this A field is perpendicular to the direction of this omega rotation direction and the r direction. So here the direction of y is simply the omega cross r, and now we turned this expression into this omega cross r, and so eventually we can the omega cross r is also along this phi direction if we rotate back the system into the coordinate over here. So eventually the answer of the A field in the coordinate system on the left hand side is the expression over here, and now we can also work out the magnetic field. So the magnetic field is simply the del cross A, and you can also eventually write down in the coordinate free expression, and you can see that the A field is actually along the direction of the momentum. So here, if you still remember, we are rotating the system along the z-axis. So all this current will be flowing in this phi direction, and the current carries the momentum along the phi direction, and so this A is also along the direction of the momentum. So there is actually some relation between the vector field and the momentum. And for the B field, we can see that it's proportional to this omega axis, omega direction, and the amplitude is also proportional to the rotation omega. So you can sort of imagine that actually there is a deep connection between a rotation and a magnetic field. So if you have heard of, or if you are doing research along the line of a superfluid or a superconductor, then you might be familiar that indeed there is actually a deep connection between the rotation and the magnetic field. So, I mean, you cannot see it from here, but there is a deep connection, and if you look at the quantum mechanics, you may know that the form of the Hamiltonian looks actually identical to each other if you carefully rearrange select your constants, like replacing the mass and the charge, the E. So there is a 1-to-1 mapping between